Hey everyone, welcome to The Explainer. Today, we're diving into a really fascinating journey to answer a super fundamental question. What is LAN architecture? We're going to look at exactly how local area networks have evolved, both physically and logically, to handle the absolute massive, complex computing workloads of our modern era. Let's get right into it. It's a question we often take for granted. We all just expect our data and apps to be instantly available, right? But how does an enterprise network actually handle millions of requests a second without just collapsing under its own weight? Well, handling that kind of massive traffic, it definitely doesn't happen by accident. It requires some seriously brilliant, deliberate architectural design. So here's our roadmap for today's explainer. First, the local area network. Second, the three-tier architecture. Third, the rise of east-west traffic. Fourth, the leaf-spine solution. And finally, number 5, future-proofing the network. All right, section 1, the local area network. So at its core, what actually is a LAN? Basically, it's a group of computers and devices that share a common communications line within a relatively small geographic area. Think like a single office building or a college campus. It's all about securely connecting devices that are physically close to each other, allowing users to exchange data and share resources on a really efficient, localized scale. To really put this into perspective, let's compare it to a WAN, or Wide Area Network. While LANs give us those lightning-fast, low-delay local connections using physical tables at OSI layers 1 and 2, WANs are the geographically dispersed networks connecting those local LANs across cities or even globally. Because WANs often rely on virtual or internet-based connections, they naturally have a higher propagation delay. They're just slower. But for the real heavy lifting of localized, high-speed computing, the LAN is our absolute workhorse. Moving on to section 2, the three-tier architecture. Basically, the old way. I want you to think of this classic structure kind of like a city's road system. First, you've got the access layer, right? That's where end users and edge devices actually attach to the network. You can think of these as your local neighborhood streets. Next, that traffic moves up to the distribution layer, which sets routing policies and aggregates the data. These are your highways. And finally, everything feeds into the core layer, which is the super fast, highly resilient backbone of the whole network. It acts just like a central interstate, connecting everything together. Now, for a long time, this model was the absolute gold standard, and for good reason. Its clear hierarchy made deployment and management a total breeze. Plus, its modularity reduced fault domains, which just means a failure in one specific area wouldn't bring down the entire network. But most importantly, it was incredibly reliable for what we call north-south traffic. That's just a fancy way of saying users at the access layer requesting data from central servers or the internet. That traffic just flowed seamlessly up and down those three tiers. Which brings us to section 3, the rise of east-west traffic, or as I like to call them, the disruptors. There's a quote from our source material that sums this up perfectly. As workloads shifted toward virtualization, cloud, and distributed systems, this model began to show its age. And yeah, it really did. The old architecture simply wasn't built for a world where applications are entirely decentralized, and servers need to constantly and instantly talk directly to one another. The contrast in these traffic patterns is actually pretty striking. Think of north-south traffic like standard commuter traffic. Users driving to a centralized server, getting what they need, and heading back. But east-west traffic, entirely different beast. Driven by AI, machine learning, virtualization, and distributed storage, it's more like a chaotic, crisscrossing delivery network where machines are just constantly exchanging massive amounts of data directly with each other. And guys, this is exactly why the three-tier architecture finally had a brick wall. Imagine server A needs to talk to server B, but you force that east-west traffic to travel all the way up through the access layer, up to the distribution layer, sometimes all the way to the core, just to come all the way back down again. It creates massive traffic jams. We're talking absolute digital gridlock. Because of oversubscription, we started seeing high and variable latency, severe bottlenecks at those aggregation points, and honestly, a system that was just way too manual and rigid to scale for modern distributed apps. All right, section 4, the leaf-spine solution. This is the new way. To really understand why this new solution works so well, we first have to define a supercritical concept, equal cost multipath, or ECMP. Basically, ECMP is a routing technique that allows data traffic to be load balanced across multiple optimized equal cost paths. So instead of relying on a single link that can easily get congested, the network guarantees high availability because it ensures data always has multiple, equally fast open lanes to choose from. No more bottlenecks. Building right on top of that idea, the leaf spine architecture actually flattens the whole network down into just two tiers. It's a really elegant design. The servers connect to leaf switches at the access layer. Then every single leaf switch connects to every single spine switch in what we call a full mesh topology. One key detail here. No servers or endpoints ever connect directly to the spine. This creates a completely non-blocking, high-speed fabric that is absolutely tailor-made for AI, machine learning, and virtualization. Now, I want you to remember this number, 2. In a leaf spine network, any server can reach literally any other server in exactly 2 hops. The data travels from the leaf up to the spine and right back down to the destination leaf. 2 hops, every single time. This is huge because it guarantees highly predictable, incredibly low latency, which completely eliminates those messy, variable path lengths that absolutely plagued the old 3-tier system. Because of this setup, the crucial takeaway is that scaling becomes incredibly simple and linear. Need to plug in more servers? No problem. Just add more leaf switches for extra ports. Need more overall network bandwidth? Easy. Just add more spine switches. You can expand the whole thing modularly without ever needing to redesign the network from scratch. It's brilliant. And that brings us to our final section, Section 5, Future-Proofing the Network. Modern networks are rapidly shifting towards software-defined models, like SD-WAN. What happens here is that the control plane, which is basically the brain making all the routing decisions, is explicitly decoupled from the data plane, which is the part that just forwards the packets. By pulling that control layer out into a centralized management platform, administrators can fully automate provisioning and dynamically optimize traffic across both local and wide area networks. And you know what? This flat, highly automated architecture pairs perfectly with edge computing. Instead of relying entirely on massive, centralized data centers, edge computing actually disperses computational tasks out across multiple decentralized nodes. And because our new leaf spine and software-defined fabrics are explicitly built for resilience and seamless east-west communication, these edge nodes integrate perfectly. It mitigates single points of failure, meaning the entire network stays robust and highly reliable, even if a few individual nodes happen to go offline. So, we've successfully moved from those old hierarchical bottlenecks to these sleek, flat, software-defined meshes. But as we all know, the evolution never really stops. As AI and edge computing continue to distribute tasks even further, I'll leave you with this thought. What entirely new emerging workloads will force the next great evolution in network architecture? It's something to think about. Thanks so much for joining me on this explainer, and keep questioning how our digital world is built. See you next time.